Hello everyone, I'm Joy Lo from National Taiwan University. I'm glad to be here to present our work, RollingStone, using single-sleeve Taxel for enhancing active finger exploration with a virtual reality controller. Recently, controller has been widely used in the virtual reality systems. These VR controllers not only are used as the input interface, but also provide haptic feedback. Compared to grounded haptic device in VR, VR controllers are not limited by the space and can be used in a larger VR environment. And instead of using wearable devices, controllers enable a faster and more convenient configuration. However, today's controller only provides vibration feedback, lacking of providing other kinds of haptic sensation. Some researchers explore different kinds of haptic on handheld device, and most of them focus on object manipulation or shape simulation. But imagine that you are playing in a VR world. When your finger moves along a table, what are you supposed to feel? So here's the question: how to provide haptic feedback during active finger exploration in VR? RollingStone proposed a new haptic interface on the controller, which creates sensation of finger sliding and surface textures. Haptic Revolver, released earlier this year, solves the same issue on the controller. Let's take physical textures on the wheel. As the wheel rotates, the haptic feature could be directly perceived. By utilizing configurable wheels and physical textures, designers can customize their own wheels in different scenarios. Instead, RollingStone generates virtual textures by using only one ball with a single texture. Designers are not limited by the physical textures and can easily produce various sleep profiles for reuse in VR applications. As a result, physical textures and virtual textures don't replace each other. The tip of using only a single ball to produce virtual texture is to program relative speed between hand motion and the ball. As your finger moves forward, the ball rotates in the opposite direction, giving the illusion of sliding over a surface. And we call this sleep feedback. By changing the relative sleep speed, we could create different surface sensation. For example, we could generate rough surface by making relative sleep speed faster, like 1.2 times the hand motion speed, or create sticky surface by lowering relative sleep speed. Moreover, RollingStone supports 2D sleeps. We could change the sleep angle when the direction of hand motion changes. The 2D sleeps provide more coherent directional cue. In order to hold and spin the ball steadily, and to properly reduce the size and the weight, we designed the prototype in an iterative process, and finally got current version of RollingStone, which is the right button one. And this is a RollingStone prototype. It consists of 2 layers. The gear motor at the top layer spins the ball to produce sleep feedback. The other gear motor at the second layer rotates the plate for adjusting the sleep angle. Both of the gear motor use magnetic encoder for measuring and controlling the speed and the rotate angle. In case the plate keeps rotating the same direction, we use epicyclic gearing design with a rotary electrical connector to prevent interwide wires. And the ball was 3D printed and evenly sanded using 80-grit sandpaper. And we use a 3D printed cast with a handle. At the top of the cast, we hollowed out an aperture for fingerprinting on the ball. The edge of the aperture could offer support, preventing finger from slipping off the ball. At last, we integrated RollingStone with HTC Vive Tracker. So this is how it looks like. Here we show 3 applications to demonstrate the capability of our RollingStone prototype. First, this application demonstrates the capability of creating various sleep profiles. In this virtual room, user can decorate the room by choosing different textures of the furniture. When the user selects textures and moves across the surface of a furniture, the corresponding sleep profiles will be generated. And we highlight the ability of creating bumpiness in this application, escape from the room. The user slides over books to find a secret book for opening a trapdoor. Bumpiness sensation will be created when the user's finger travels gaps between each book cover. And when the user finds the most sticky book cover, he pushes the book into the bookshelf and opens the trapdoor. We can create not only long-term sleep, but also short-term and rotational sleep. In the Ninja survival game, the user throws darts to the approaching enemies. At the moment the user throws the dart, they feel short-term sleeps and rotational sleeps generated by RollingStone. User can also change the darts in the menu for perceiving different textures. But how do we design sleep feedback to generate textures, bumpiness in these applications? Before designing applications, we encounter several challenges. The first is, does sleep enhance the sensation of sliding? How to adjust parameters of sleep to create different textures? Moreover, how well can participants discriminate relative sleep speed and relative angle between the finger and the sleep display? For answering the question, we conducted an exploratory study. In this study, we designed 6 sleep profiles. Participants experienced these profiles and then rate the subjective scores about sliding sensation and 3 texture properties, namely roughness, bumpiness, and adhesiveness. 6 sleep profiles are composed of 2 factors, 3 relative sleep speed and 2 speed variation. Relative sleep speed and speed variation are both important parameters of sleep. Relative sleep speed is the ratio of the both sleep speed and the hand motion. We select 60% slower, that is, sleep speed is 60% lower than hand motion. 0%, which means sleep speed is equal to the hand motion speed, and 60% higher. And 2 speed variation were chosen. One is without speed variation, that is, relative sleep speed is constant. The other is with speed variation, which means relative sleep speed changes as hand moves. So the procedure is, the participant first explores 6 profiles in order, and were asked to describe how they feel. Participants then were given 12 nouns related to the textures. They were told to select the nouns that are most close to their feeling. After that, they rate subjective scores on sliding sensation and 3 texture properties. Finally, they can freely explore 6 profiles to adjust the score. Here's the result of sliding sensation. The results show that participants felt like sliding over a surface using RollingStone. But the profiles with speed variation received lower scores. Based on the reports of the participants, it is because they really encountered periodically changing textures in their daily life. And here's the result of texture properties. The results show that both relative sleep speed and speed variation have effects on the perception of 3 properties. For example, higher relative sleep speed increased the sensation of roughness. Participants felt like they are swiping over the wood or rough stone at higher speed. Slower relative sleep speed increased the sensation of adhesiveness. Participants report it's like sliding on the rubber, and some said the virtual surface dragging on my index finger. And speed variation increased the sensation of bumpiness. 3 participants report their finger moves up and down when they are experiencing profiles with speed variation. Now, when we are going to design haptic feedback, we understand how to change sleep to create different textures. Still, we don't know how well can people discriminate two sleep profiles. So in the second study, we want to know how precise can users differentiate the sleep speed under combination of hand speed and relative sleep speed. We use J&D staircase method. For further explanation, participants slide over 3 surfaces. One of the surfaces has a different sleep speed. Participant has to answer the different one. If the answer is wrong, the variation between 2 sleep speeds rise. And if the answer is correct, we decrease the variation between 2 sleep speeds. When the variation between 2 sleep speeds converge, we got the sensory limit of sleep speeds. Here's the result of average variation between 2 sleep speeds. We found that the hand motion speed doesn't affect the sensory limit, which indicates that designer can design sleep profiles at any hand speed. The result also suggests that relative sleep speed has an effect on the discrimination of sleep speed. That is, when designing the profiles to make 2 textures distinguishable, larger speed variation is needed under higher relative speed. Now we got the sensory limit of relative sleep speed. The last unknown answer is the sensory limit of sleep angle. But why does sleep angle matters? Ideally, sleep angle should follow the direction of hand motion. But whenever the direction changes, it leads to undesired rotational sleep of prototype. So we want to know in which angle will participants find out there is non-consistent between hand motion and the sleep. The procedure is same as the previous study. Participants slide over 3 surfaces. One of the surfaces has a different sleep angle. Participant has to answer the different one. The results show that the average threshold is 53 degrees. That is, when designing applications, we could change the sleep only if the angle between the direction of hand motion and the ball is bigger than 53 degrees. Finally, to ensure if the sleep feedback is a valuable haptic addition, we conducted an evaluation study. Participants experienced 3 applications with and without sleep feedback, then do a questionnaire rating the realism and the enjoyment. The results show that sleep feedback can increase realism. And for enjoyment, sleep feedback receives significant higher scores in Decorate the Room and Escape from the Room, but score shows no difference in Ninja Survival Game. We also receive feedback from the participants. There are positive feedback, like some do feel textures, gaps between books, ways of darts, or sleep making games more exciting. And also negative feedback. For example, participants report that the sleep feedback was not important in the Ninja game, giving insights that short-term and rotational sleep may be too short for enhancing enjoyment. And there is a participant thought that the experience of textures were not coherent to the visual feedback, which indicate a more careful design is needed, or we could build a sleep profile texture rendering algorithm in the future. To sum up, we use sleep feedback to simulate slide sensation, and by programming sleep feedback, we can generate different surface textures. We conducted 3 studies to understand how participants perceive sleep feedback and their sensory limit of sleep display. This study gives insight of later design. Finally, we implemented 3 applications for demonstration, and user evaluation shows RollingStone as a valuable feedback. Thanks for your listening.
There are 2 microphones, one up here, one over there. Please line up behind the microphone if you have questions for Joe Yulo. I will get us started. So you presented slip textures. Have you thought about combining that with some other tactile methods and what you could do if you incorporated something like vibration?
Yes. We have to think about it. Like combining with vibration, we can simulate the sense when you touch the surface. But after that, when you are dragging the surface, then we use sleep feedback, something like that.
Okay. Have you thought about how you could leverage the finger movement with the slip texture? Because right now you're using sort of the whole hand movement as that's moving across. What if the user wants to sort of move their finger independently of their hand?
No, we can only. Now, user cannot bend their fingers, but maybe in the future we could make the device more smaller, and the ball can only put under the finger, and they don't need to hold the handle, so they can bend their finger or do whatever they want.
Makes sense. Anybody else? All right, let's give Zhou Yulou